Okay, well, we looked at addition and subtraction formula. And what came after that formula? Half angle formula. Excellent. Well, actually, in between, I think that was a double angle formula. That's what we did last time. We did with this one first, double angle formula. I'm not thinking clearly. It's double angle. Double angles are sine of 2x, cosine of 2x, those things. Do you know what we did after that double angle? There was one more power lowering, right? That's right, the power lowering formula. And we use this power lowering formula and addition formula and subtraction formula, which is called product sum formula, but we didn't memorize. It's just a method. From there, we did something called free analysis. Can somebody explain analysis? What this free analysis is? What are we doing with the free? I give you trigonometric functions such as sine 2x times cosine 3x raised to third power, things like that, right? Algebraically constructed from, right, write it as a sum of pure waves. Now what's complicated calculation? Well, once you have that, it's great information physically. Also mathematically, it's easy to do calculus. That was free analysis. We use power lowering formula and we use addition and subtraction formula to write it as a sum of pure waves, right? A times sine 2x, b times cosine 5x, sum of those, not product. Okay? Then last time, from, I think, power lowering formula, what do you think? From power lowering formula, we have half angle formula. Does that make sense? We looked at the power lowering formula of sine squared, cosine squared, and turned that easily into half angle formula, right? Okay? What did I do with that half angle formula then? We're able to create all the approximate values of a cosine and sine. So tables of cosine and sine value. Right? And I showed you how to do that with a computer. Think about it, you have this algorithm that you can add and subtract and compute square root. With that, you can go to cosine and sine, right? And I think I linked that to the tutorial, so I shows you how to do that with a computer program. All right, that was actually important. This is some fundamental facts about how sine and cosine interact. From there, if you think one at a time, there is simple things that follow, and that has this very interesting application. Free analysis, one of the most important business in science and technology and mathematics, and tables of sine and cosine value. Awesome. All right. Now, also in calculus, we solve equation. This is how you actually use it, but in many algebra mechanical setting, we solve equations. So we're going to solve trigonometric equation. That's the next part. All right. So here's trigonometric equations. So we're going to look at most fundamental equation, and when you enter this one, I want you to look at this sine and cosine as a motion function, not angle function, and makes more sense, right? So question on motion. This is going to be all sine and cosine. There's really no motion, but if you look at it as motion, and the way we solve this equation makes more sense, right? So here's some fundamental equation. With this fundamental equation, plus some algebra, plus some identity we thrown in, that's going to take care of this section and next section. All right. So here's some fundamental equation. sine of t equals a. That's a trigonometric equation. And solve, so let me correctly phrase it here. We want to solve this equation for the variable t. A is given. Sine of t equals 5. Can somebody solve that equation? Sine of t being 5 without touching calculator. What kind of value of t? Sine of t being 5. Sine of t being 5. If you don't touch the calculator, all you know about the sine t and cosine t is on unit circle. That's where things are, right? So think about an angle for which the sine value is 5, sine of t being 5. What angle is that? First and the second quadrant. So here is your unit circle. Okay? So you go around, you start in here, go around all the way around in here, and where is your y equals 5 on the unit circle here? 90-degree angle. What is the y coordinate here? It's 1, right? So that's not 90 degree. Where is it? It's not on there. That's the important thing. There's no angle for which y coordinate is 5. So if I put 5 in there and try to solve it, and you hit the calculator and you realize it, oh, it's error, undefined, and things like that. Alright, so this equation, sine t equals a, is only meaningful when you put a value. What kind of value? Less than 1 and greater than negative 1. Well, y coordinate can be negative 1 all the way down there, right? So y coordinate must be 1 and negative 1. Okay? So if this is outside 1 and negative 1, it's easy to solve, right? Doesn't exist, so doesn't exist. But when you pursue mathematics and learn more about this interesting function, and you will see the sine t equals 5 is solvable in complex numbers. It's very interesting. Anyway, sine t equals 5 is not solvable in the world that we can quite clearly see in here. Alright, so that's the equation. So how are we going to solve it? Most of the time you're going to use a calculator unless this is very special value. Anybody remember a being special value? Who remembers a special value? 1 or 0 is very special value. Okay, if I put sine t equals 1, what do you see? What kind of t value do you see in the circle? Sine t equals, a is 1. Is that easy to solve without using calculator? What is the angle? 90 degree, right? And that's the only angle in there, 90 degree, right? But t is not angle, right? T is not angle, t is time. So think about, keep circling around, and you have to, first is 90 degrees, so answer is not 90 degree. What is the correct answer if it is in motion? Pi over 2. Pi over 2 seconds later is here. And when is it coming back here? 2 pi second later. So pi over 2, 2 pi plus 2 pi, and pi over 2 plus 4 pi is keep coming back. So how many solutions are there? Infinitely many, right? You can even go time backward. So there are all solutions. How about 0? Do you see 0? When is a sine t 0? X-axis. Here is a 0 and here is a 0. So when is the time in here? 0 second. And pi seconds later is 0 again. 2 pi second. 3 pi second. 4 pi second later and 6 pi second later. This is keep going 0 and 0 and 0. Those are all infinitely many solutions. Think about graph and x-intercept and stuff like that. Alright, these are the easy to, what other values do we know that is easy to answer? Coming from special triangle. 45 degree or pi over 4 special triangle. What are the sine values? Over square root of 2, thank you. So if this happens to be 1 over root 2, without touching a calculator, you know some answers to that, right? Okay, what is that? Pi over 4? Right here, pi over 4. Okay? If you go over here, is that still pi over 4? I mean, is still y coordinate the same? It's the same height, right? So that's the same. But calculator won't tell you this. You have to figure that out. Calculator will only give you angle in first quadrant and fourth quadrant. And in this one, we didn't even use a calculator, but you know this across there, there's another angle. And then 2 pi to that one, this one, and 2 pi. So there are two types of solution, but there's infinitely many. But keep adding this 2 pi, integer multiples of 2 pi. What other special values do you know? Pi over 6 and pi over 3, those are 60-30 degree, right? I think they were 1/2, if you look at that triangle, and root 3 over 2. These are it, 1 and also -1 here. These are the special angle you can easily calculate without using calculator. Other than these values, we have to use a calculator, right? Okay, so here's how you solve it. Let T0, it's a special solution, T0, special solution. We're going to set that one sine inverse of A. So you hit a calculator. What kind of angle sine inverse you're going to get? Sine inverse, if you hit a sine inverse, it doesn't give you an angle that is in the second quadrant or in the third quadrant. Sine inverse will only give you pi over 2 to negative pi over 2, right? Okay, so we have, for example, an angle in here. We found it. But you know, across there is the same y coordinate there, right? So we know there are one more angles in. How do you get to that? If I have, let's say, here's a 1 radian here, or 0.5 radian, how do you get to the other one? 180. So here's a pi. Okay, so another special angle T1 is pi minus that one you just calculated, right? So I'm just going to write it like this instead of T0 so that you can kind of see. Sine inverse is what you get from a calculator or from special triangle. Then you have to consider these two fundamental ones, that is in between 0 and 2 pi. T0 is here from the calculator. Another one is pi minus this one. Is another one, right? So these are the two things that you see on the unit circle. But how to get more? It's the time is keep circling around, right? So general solutions are like this. T is either sine inverse of A plus what? 2 pi, that's right, 2 pi. But you can keep adding a 2 pi, so we write it like this. 2k pi, integer multiple 2 pi k. I think they write 2 pi k. It's better be consistent here. Let me change to n. It's more suggesting that n is a integer. This n can be negative number as well, right? Don't think these are the same number. These are different numbers, right? Happen to correspond in the same position on the unit circle. Does that make sense? Right. And there are one more. What are the other kind? Pi minus sine inverse of A plus 2 pi n. This n and that n is not kind of the same n. It is just a parameter that is involved in there. Okay? Well, let's say in this section, whenever we use this n represent integers. So we're going to omit this one, n being 0, plus minus 1, and plus minus 2. N is this type of a number. Rather than keep writing this one over and over, we're just going to assume n is this integer all the time. When n is happen to be representing something else, then we have to specify n is something else. Other than that, we're going to assume n is representing this integer, signed whole numbers, or something like that. All right? So this is how you solve it. Whenever you see this equation, sine t of equals a, and you're solving for t, you hit that sine inverse of a. Think one more time. whether is a special of angles and handle that special angle exactly for whatever sine. And in my class, during the lecture, we're just going to use sine inverse A. All right? We did a lot of these special angles, so you should be able to handle. And you can cheat when you're doing the Weber sine. There are a lot of ways to figure out this one exactly. So deal with it. Okay, this is the idea. Is that okay? All right. Number 2. What's number 2? Any question about do you think it kind of answer completely? This is it. I hope you understand that. If there's any value, you plug in 2015, and I got this value A, it must be in this form. It must look like this. All right? So what is the second equation? What kind of equation you want to solve? Cosine, thank you. Cosine of t is going to be A again. Is that okay? And make sure you feel comfortable with dealing with the radian here. So motion, t is a magnitude of time. You've got to deal with the pi over 2 and things like that. All right. Let's go back to circle again. This is the same, right? When a is at 1, 0, -1, and these values, then you can calculate t special value, special solution, a particular solution of t exactly. But in general, suppose we found 1 from a calculator. So cosine inverse, right? We're going to hit cosine inverse, right? Then what kind of angle the calculator give you? First quadrant and second quadrant. Remember that? Yeah. So that's where cosine value, x coordinate does not repeat. Right. So if you have it here, and it's not going to give you, this is different cosine value, right? Opposite. Where is angle that has the same cosine value, same x coordinate? It's down here, fourth quadrant, right? So if I have t equals 0.3 radian here, what is this one in here? Down here across the x-axis. Negative 0.3, does that make sense? 0.3 radian there, down there's negative 0.3 radian. That's the two angles. So we have two particular solution that we're going to get. Here's a solution. This is how you solve it. I have one solution from calculator, and that's going to tell us the one angle in radian, right? And what is the other angle? If I remember how to get the other angle. 0.3, you got 0.3 from calculator, and what is the other one? Negative 0.3. So negative cosine inverse. Calculator won't tell you this. You have to figure that out. Right? All right. So we have this two angle. That's the only angle that kind of coterminal, different, not coterminal in that angle. Those are the two angles. All the other thing is integer multiple of 2 pi n. So how does this t look like? Is either came from cosine inverse a there plus 2 pi n, right? How about the other one? Minus cosine inverse a plus 2 pi n. As you put this various different integer value of n here, you will get these two different kinds of value. They are all solution to this equation, cosine t equals a, right? And if you get used to this mechanical procedure of this one, once you understand it, when you go to a higher level of equation, it really makes things easy. You don't have to keep thinking about everything and juggling in your head. That's why we're doing this mathematics, developing this method, and you understand why it works like that. Once you understand, you put it aside. You don't want to think about it anymore. You just rely on the machinery, and then you efficiently handle the problems, right? But, often, and we forget about this understanding part, and it's too much focus on the machinery, you end up at not understanding what's going on. So you have to balance out these two things when you learn mathematics, and it's always fun, as far as I know. Okay, Rodney. Go ahead and find the old solution in between negative 2013 to positive 300. Find all the solution within that. You know it looks like this, so it's really easy to handle, to figure out what kind of n we have to plug in. But this is most general solutions. No, I think we just better look at one problems and then from there. But it's a very good question. This is most general shape of the solution. If they want t ranges, I want this phenomenon happening after 3 seconds to 35 seconds. How many solutions are there in between 3 seconds and 35 seconds, right? And we're going to use this one to figure out exactly what number fall in. And this will be perfect information. All right? We'll look at an example. Is that all right? Okay. Or in between 0 and 2 pi, and that would be really easy. But that's the application. So I think this is one of the first examples. You see, you're given an equation. There are infinitely many solutions. All the polynomial equations and exponential logarithm, you have an equation, you expect there are usually 1 or 2 or 3 solutions, right? And we're looking at how many? Infinitely many. As we vary this n, there's just infinitely many. Think about horizontal line, and the sine curve is keep hitting that horizontal line over and over again. So, right? Yeah, things like that. All right. So, number 3. What do you think? Solve tangent. That's right. This actually occurs a lot in engineering and physics. And A here for t. Again, what is the, don't just a calculator, what is the solution to cosine t equals negative 3? Cosine t equals negative 3. Cosine t equals negative 3. There's no answer. It has to be in between 1 and negative 1. How about tangent t equals negative 3? What does tangent t represent in geometric? Slope. Is there on the unit circle the slope is negative 3? Yeah, right. If you go to vertical, almost vertical, then it's going to cover all the large number and every number in there. So you can put any number in here, A, then there will be a solution, right? Is that right? All right, let's go to circle and think about tangent inverse. You're going to hit tangent inverse to get an angle. They give you first quadrant and fourth quadrant, remember? All right. All right, if I have an angle in the first quadrant, where do you see there's another angle that has the same thing? Same slope. Which quadrant is it? Fourth quadrant here is the same slope? This slope and that slope is the same? I don't think so. So look at it here. These two lines are the same slope? No. There's a third one. If you extend it, that's the same line, right? It's the same slope. So how do you go from here to there? Add pi radian. So solution goes like this. I have one special solution. You calculate this one. What is it? Tangent inverse of A, right? You got that number. And unlike the other one, we can calculate a t1, and it's a pi. And it turns out is rather than doing 2 pi, this is sufficient. Just you look at one angle and get 1 pi and another pi is keep going around the same. You can apply this exact same principle here, but by looking at the actual solution, you realize the tangent has actually shorter period. Tangent period is not 2 pi. It was a pi. Remember that strip? The length between those two vertical asymptotes were pi. So the period of tangent is not 2 pi, but pi. So with that, you don't have to do t1. It's a lot simpler in here. In general, for this case, t is this tangent inverse you see in here, and plus, what do you add? What is the period? Not 2 pi, but just a pi. Like this. In tangent case, there's no 2 case. It's just 1. Why is it different? because the period is pi, and this two special solution is obtained by going another pi. And therefore, it happened to be in this pi kind of shift. All right. So there's a slight difference in the tangent solution. It's nicer. This is it. This is most fun. We're going to be using this over and over to solve more complicated trigonometry equation that involves. We're going to reduce that equation down here. Reduce is a better word. All right. So let's start with the actual example. I want to start with example 3, the real example that is not special, right? So here it is. All right, none of these things will be given, right? So let's use this as an opportunity to think about, all right, there is cosine theta equals A. Then you're going to hit cosine inverse, right? That's easy. And keep that into 4 decimal places in radian, and think about what to do, right? That is not the only solution. You're adding 2 pi and that part's easy, but there are 2 solutions for cosine, two type of solution, right? Try to remember the principle. See if you can derive that formula that I introduced. Okay, I hope this makes sense, right? And pay attention to the T1, and remember, when this is a tangent equation, there's no T1, right? Only one special a particular solution you get from calculator and just shifting by pi. Any question about this one? Fair enough? Okay, I think it's quite the same with sine. So why don't we make this exercise? Let's do it quickly. Solve sine t. So I don't like this theta business. It has to be t, right? Although they use theta, it doesn't mean it's angle. Let's switch the sine t. It's a better sine t being 1/3, and solve tangent t being 3. These are 2 exercises I want you to go through. Solve sine t being 1/3, tangent t being 3, right? Both are solvable. Tangent t can be anything. It's your exercise. Is it okay? Oh, this is it. Okay. Although we use this particular version that I sit down, there could be different version of this one, right? For example, if you go back to cosine in here, I'm using the negative angle there, right? Think about this being negative 45, but someone like to use a 360 minus 45. What is that? 360 minus, is that 315 or something? Right? 315. So someone can use, instead of negative 45, 315 is also valid version. So instead of putting, this negative number, someone might like putting that large, whatever that, 7 pi over 4 instead of negative 4 pi over 4. Does that make sense, right? It's about that idea. Is that all right? Okay. So that's that. Now, if you have this type of equation, then and we're going to solve it. So let me go straight to this quadratic type. You can imagine that you're in some engineering and physics problem that sine and cosine shows up, whatever the law that you want to satisfy, and you end up with this type of equation. So let me read out this equation. They said it's a quadratic type, right? I hope you see this. There's some squared involved and things like this. Let me restate this question like this. It means this cosine t squared minus 7 cosine t plus 3 equals 0. That's the equation we're looking at here. Right? that make sense? Cosine squared t. So it's really about cosine t, right? So you have to break this one out in the second level. So you can really look at it as a, all right, we're going to substitute this cosine t equals a like this. And this equation becomes 2 times a squared minus 7 times a plus 3 equals 0. Is that right? If I call that cosine t commonly appearing part, if I substitute with a, it's 2a squared minus 7a plus 3. So we're going to first find this value of a, solving this quadratic equation, right? Then what? Then once you have this a, go back in here and try to solve these equations. Okay? So let me make that part an exercise. One step exercise is to solve this equation in for a first. Forget about cosine t. This is the same old quadratic equation. And that's your first exercise. Okay, they gave this wonderful quadratic equations, so factoring works. But that's for the classroom, right? In general, it usually doesn't factor, and the number is not even like the cleanest, like 0.2 or whatever, or lambda, things like that. So how would you actually approach that? The quadratic formula is most efficient. I don't want to go back to explaining why quadratic formula works and things like that. Let's just use it, right? Is that okay? So this is how I approach quadratic formula. D, first compute b squared minus 4ac. That's the part that you get out of completing the square of this expression. So b is negative 7 minus 4ac is a 2 and 3 goes in there. So this is called discriminant of this quadratic polynomial. 25 negative b plus minus root that discriminant divided by 2 times a. That was the quadratic formula. Okay? So let me write that down. I forgot to write that down. A is supposed to be negative b plus minus that d you just prepared divided by 2 times a. A is the coefficient of a squared. B is the coefficient of a. And you have to put the negative. These numbers gives you 3 or 1/2, which you could have obtained by factoring it, right? Is that okay? That's called quadratic formula. And this is something that you have to remember. What is D? Name for that? Discriminant. And what is the formula for that? B squared minus 4ac. That's underneath that quad formula. That's quadratic formula. Handy. And this one more thing to memorize. All right. So we got A. A can be 3 and a can be 1/2. We're going back to substitution. Back to our original problem. Back to what? Substitution. Who remembers the substitution? Originally there was a trigonometric, what was it? Probably, I boxed it, right? What was the substitution? Cosine t being a, right? So what's a here? Can be 3. Or cosine t can be 1/2, isn't it? Right? So if this were 1/3 instead of 3, you have 2 trigonometry equations. For both of them, you have 2 kinds of infinitely. So we have 4 kinds of infinitely many solutions. Does that make sense? But here is cosine t is 3. So you know about cosine t equals 3, right? It's not solvable. 3 is too big. Okay? So you're going to state clearly here. All right, cosine t is not solvable. So we don't have to worry about that equation, correct? And if you organize neatly, it's possible. It's better when things branch out to more and more cases like this. And the second equation is meaningful. Cosine equals 1/2. All right? Web assign wants this one not using the calculator. Do you know why? 1/2? That was a special value. That came from pi over 3 and pi over 6. So WebAssign wants that answer here. Okay? But we're just going to hit calculator here. So let's solve from here. This is your exercise. Again, if these two are both solvable, then we have to just put them all together. They're all solutions, right? Here, we got only one basic trigonometric equation. So complete that part in here. We'll just use the decimal answers. How was it? Was it okay? Yeah, so here's the two types of not two solutions, two types of infinite solutions, right? And there can be two more if this were small enough. 1/3 is small enough. Any question about this quadratic type? Yeah. Let's do some example then. All right, here I pulled out exercise. It says, let me write it a bit bigger. So why don't I change that to squared? So let's focus on the square part. So I changed it. So it's a tangent square theta minus 13 tangent theta plus 36 equals 0. So also, I'm going to change that to t. All right. Solve this equation in t. This is a quadratic type. That's the key thing that you're supposed to notice here. All right, did it go okay? So there are two cases because the tangent, it only gives you still one type each. So we end up in here. But if this were cosine t 1/4 and cosine t 1/9, then you can see there are four lines, right? Does that make sense? 4 lines. If it is a sine, also it's a 4 line. There's special cases that even if it is a sine equation, you only get not the two types, only one type. If it is over here, you can see that's the only angle. Extreme case, only angle on the unit circle has that sine value. Other than that, there are always two, and another one in here. Okay, so occasionally you end up at one line for each sine, and you know that's pi over 2. All right, but most of the cases you always have two types for sine and cosine. So that's some examples. Okay, I'm gonna save this one and do more of this section. Okay, I copied that problem, and that wasn't exactly the problem from the book. Problem from the book, it was a little bit more complicated. So we're turning to that problem 44. Okay. Problem number 44 was actually solving tangent to the 4th power t minus plus, what was that? Minus 13. Minus 13 tangent to the t plus 36 equals 0. Squared here. Before it was a tangent squared and tangent. This time is a tangent to the 4th and tangent squared. All right. You still see, although it's quartic, degree 4, do you see that it's still kind of quadratic type? Can you make a substitution in here such that you can still turn this one into quadratic equation? Yeah, so let's write that down. I think it seems like Eva has an idea. Let's listen to her. What is our substitution? What is going to be our b? Just distinguish it from earlier. What is b? Tangent squared t. That's our idea. Let's see how it's fit in. This is our original equation. Tangent to the, so this tangent squared is really tangent t squared, right? That's what it means, right? And our equation here is really tangent to the 4th minus 13 tangent t squared plus 36 equals 0. This is our equation, and one suggestion is that why don't we look at this tangent t squared in here and call that b. Then this one will be b, and the other one, if that's a b squared, and that's great, right? Rather than turning this one into the b squared, just check what the b squared is going to be. And if that agrees to that, and it's easy, right? That's your choice. Some little bit of, I don't know, intuitive choice. And you don't have to turn this one. See if b squared is there, right? So what is b squared here? Tangent to the t raised to the fourth power, right? That happened to be right there. So you know that's a b squared. So this one changes to b squared minus 13b plus 36 equals 0. Okay? Make sense? Again, go for that substitution and don't try to change this equation and manipulate it. What you want is that either b and b squared showed up. So calculate b squared and see if that can be, replaced and substituted back in a completely quadratic equation in b. All right. So let's cheat a little bit. Here we know what b is, so I'm going to do dot dot dot. We already did this equation, right? What was b? I think that was a 4 and 9. 4 and b equals 9. We use a quadratic formula to get that one, or factor, however you get this one. 4 and 9, right? Any question? But when you come back to the substitution, what happened in here? It is not tangent t is 4 or 5, 4 or 9. It is a tangent t squared is 4, right? So that's as a bullet item. We're going to take care of this equation, and we're going to take care of tangent. Let me just write it here onto tangent t squared equals 9 as well, right? That makes sense? You have to do this one separately. This is not yet basic equation. Let's look at it here. Bullet item here. We want to solve this equation, tangent t squared being a 4. This is also a quadratic equation, but it's very easy to solve. This quadratic equation is easy to solve. What would you say? Yeah, the tangent t is positive 2. Thank you. Being remembered to putting that both positive and negative thing. What if this were 3 instead of 4? Plus minus root 3. If this is 5 plus, and so on. Just putting the root in there. Okay? Then you have a 2 equation. You see that? Tangent t being equals 2 and tangent t being equals negative 2. Right? So you have to solve these 2 equations now. All right, let's look at the other one. Tangent t squared equals 9. What do you see here? Tangent t being plus minus 3. Then you have 2 basic equations to handle here. So how many basic equations do we have now? 4 equations. Each of them, you have to apply that very first thing that we did today. Okay? So let's do that here. Finish it. Exercise. Finish the solution. Is that okay? When you're solving tangent 2 and tangent t equals 2 and tangent t equals negative 2, and the fact that you're getting this one answer and negative one answer is not coincidence. It's always like that, right? But you have to know clearly which one works like that and which one doesn't, right? It's not always like that, right? It's about even and odd property. Remember that part? Yeah. Don't abuse it. That's what I meant. All right. Any question about this problem? Does that make sense? So you have to recognize the quadratic type and try to break it down to this fundamental shape, and then keep applying that thing that we did discuss at the beginning of today's class. All right. They have many more. All right. Here's another problem. All right. This is not just the cosine, right? But a mixture of sine and cosine. So can't just change it to quadratic type, but always look for some common part. Maybe that's going to give you some idea. What's common in here? Cosine theta is common on each term, right? So what comes to your mind? If you see common thing? Yeah, the factoring out, right? So I'm going to do substitution again to help you see this factoring out. Some of you just see this immediately, some of you don't. So that's why I'm doing this one. So this part is not quite necessary in the test. I'm going to call that common part called cosine theta b, right? Then equation becomes, all right, how about 5 times sine theta times b plus 4 times b equals 0. Isn't that the equation in here? Correct? Then we factor out b, right? Like we have. Let's see if we can fill out. What happens if you factor out b from the first term? 5 sine theta? Is that okay? How about the second term? 4 equals 0. Okay? So this is not a quadratic equation or anything, but it is the important idea when you're solving an equation. Product equals 0, right? Then either one of the factor must be 0. Okay? Let me say this again. I have two numbers, x and y. I multiply it was 0. What's the possibility? Either x was 0 or y was 0. There was no other possibilities than this, right? Or both are 0. If you multiply non-zero, you will never get 0. So you multiply two quantities. One is simply denoted by p. The other one, whatever that thing is just one quantity put in the parentheses. So what is the conclusion from here? Logical conclusion that everybody has no doubt about it is that either b was 0 or the second guy, 5 sine theta plus 4 is 0. That's the only possibility. That's the merit of a factoring when you solve equation, right? That when you factor quadratic, that's the same idea. If you have a quadratic equation, you factor into linear, then either one of the factor must be 0, and that gives you the typical method of solving equation by factoring. Does that make sense? All right. Now, this is not quite the equation we have looked at yet, but do you see that if you can isolate sine theta? Right? So then it's going to be a typical equation, right? So that's where we're going. So let's not skip things in here. Let's do it systematically. What was b here again? Cosine theta equals 0, right? So that looks like something we can handle, correct? Even 0 is a very special angle, right? All right, what about this one? Can I write it sine theta equals something? Somebody already did that? What was the answer? Minus 4/5. Okay, you can isolate sine. If it's a linear, it's easy to isolate it here, right? Any question about this step? So have we arrived these two equations we can control? Cosine theta, that was the basic kind. Sine theta equals -5/4. No problem, right? So let's finish this one. That's your exercise. Okay, so I have these 4 different types of infinitely many solutions, and that's all the angles that makes that original equation 2 times sine theta cosine theta plus cosine theta equals 0 satisfied. All right?